Right. Now, the next type of projection that I want to talk about is vector projection. What do you think, conceptually, in our guts, the difference between vector projection and scalar projection is going to be?
Oh, it's going to be a vector, not a scalar quantity.
Good, it's going to be a vector, not a scalar quantity. Nice answer. What does that mean I have to add to my answer? I have to add a direction. Now, if I'm projecting A onto B, what direction is my shadow?
Same as B.
Same as B, parallel to B. Are we all okay with that? So we've chosen B as our base vector in this situation, this one here, and we're shining A down on top of it. And so any shadow that we get is going to be in that direction of B. So we need to take this definition and we need to turn it back into a vector. So to do that, we can say, and I'm just going to write it up here as well. Remember that we said that this was equal to A times the dot product unit vector B, because that's in the direction of B, and it was that, because I haven't done my things. Right, there we go. So we can then say, for a vector projection, that C, which is a vector, is going to be my A vector dot my unit vector B. So that's the scalar projection in the direction of B. But that is a scalar quantity because dot product gives us a scalar. So I have to then say, and I'm forcing you to be in the direction of B. And our unit vector does that really well because the unit vector has no length, or one length, but nothing that will change the length that we get from here. So this is our magnitude in this direction. Does that make sense? We can then go on to sort of unpack all of this. We can say that this is A dot B over, because we're going backwards on this one, over B. And this one here is also B over B. So there's my two unit vectors hidden in there. And I know that one seems like a little bit of a palaver because it's just gone backwards from unpacking our unit vectors. Okay? Now, this is technically this, but it's a dot product, so we're going to get a scalar quantity anyway, which is why we did this vector's dot product down the bottom here. This will get us a scalar quantity. Are we okay with this? Yes? So literally we just said, find me this magnitude, but I'm forcing you off into that direction. We okay so far?
Yeah.
Question?
Won't they cross off?
Won't these cross off?
Yeah.
Not when you're doing the dot product, because we can't factorize out B as a dot product, so we can't cross off.
So B dot B would be magnitude of B squared.
So this is the magnitude of B squared.
And then above that, that would be A dot times the magnitude of B squared.
Here, no, because we've done this operation first.
Okay.
And remember, division doesn't work nice and commutatively, okay? But really nice thinking. So it doesn't factorize out, we can't do a cross out, they're dot products. So of course, if we have our vector B direction, and I've got my vector A that I'm projecting down onto it, and I've projected A down to the horizontal here, and it's now a vector because I've forced it to be in the direction of B. So here we have our A dot B dot unit vector B dot unit vector B. We also are interested in the other component, the one that adds up to being our vector A. Now, because they're both vectors now, who wants to have a stab at the formula for this direction using your knowledge of vector addition? This one and this one add up to this one. So what's this one going to be? Hint. This bit. Agreed? You're all like, no. Because these two just add up. Now, of course, if you knew this was 5 and this was 3, you'd know that this was 4. Do you agree, by Pythagoras' theorem? But they're all scalar quantities. Even though I've drawn these really nicely to be horizontal and vertical, they don't need to be. The only thing they need to be is perpendicular to each other. A special note here, you've already been doing this with your component form where you resolved something into an I and a J direction. I and J are perpendicular to each other. They're both unit vectors, so you've actually already been doing this. It's just formalizing that notation a little bit more. And of course, who wants to be writing projection of A onto B all of the time, which is the correct thing? We do actually come up with a nicer way of doing that. But if you're a mathematician and you're thinking, how will I change projection of A onto B into some sort of shorter symbol, what would you do? If you were abbreviating this, what would you do?
Takes the first 4.
Cheater. It's got spoilers over here, so just ignore him. What would you do? What would you do?
Make it proj.
Make it proj. Some of you already know. We make it the projection. And how are we going to tell you the direction of the projection? I gave you a bit of a hint earlier when I said base B. Not logs, but we're going to use very similar notation. Why did your brain go to logs? Base B. So we're going to go base B of A. What would this one be? So, small story. Last year, about half an hour before the HSC is going in, I get a very panicked student to the door of the staff room going, "Miss, is it Proj AB or Proj BA?" And I'm like, "I'm sorry, what?" And they were trying to work out which way round it was. But if you remember that it's just like logs, and it's the base, and that means we're projecting A onto B. This means we're projecting B onto A, just like we would have in our logs.